All right, guys, back at it again. Okay, this week we're definitely going to be working on trig equations. We'll see how much we get through. We might get through all of it this week, or we might have to extend this in the next week. So a trig equation is just what you would think. It's an equation that involves a trigonometric or multiple trigonometric functions, okay, and we're looking for solutions for it, okay. So something as simple as this, sine of x equals 1/2. And so, we want to figure out, okay, well, what values of x will this work for? What angle measures would work so that I take sine of that angle measure and get 1/2. Now, one of the ways to look at this is, what if we took a graph of sine of x and we put the horizontal line through it at y equals 1/2. Okay, so that's y equals 1/2. Okay, so everywhere that the graph of sine of x intersects that horizontal line, y equal 1/2, would represent a solution. So we look right here. Okay, I've got a solution right there. Now that would correspond down to some x value here. And we say, okay, well, whatever that x value is right here, the sine of that has to give us 1/2. And you say, okay, well, we'd have to have a solution here. And that would correspond down to some x value, which again, we take the sine of that x value, and obviously we're going to get 1/2. Okay? It's going to happen here as well. This x value right here. Well, the sine of that x value, whatever it is, has to give us 1/2. And the same thing happens here. Okay, that would correspond down to some x value. Okay, and so the sine of that x value would give us 1/2. So you can see you are going to have a whole bunch of possible solutions. And we usually do one of two things here. Okay? The first one, we limit, what are our solutions in one period of the trig function. Okay, so sine has one period going from 0 to 2 pi. So you'd say, okay, what are the solutions from 0 to 2 pi? And so we would just be working here. And clearly you're going to see you have two solutions there. Okay? Or another way to deal with it is we say, okay, let's solve it on the set of real numbers. So we say, okay, we want to represent, all of those solutions. Okay, so we say on the set of real numbers, what are all of the solutions? Well, obviously, if I continue this graph to the right and I continue this graph to the left, I'm going to just keep adding solutions. They're just going to keep recycling themselves because sine just keeps oscillating up and down between -1 and 1. So I would have to come up with some way to represent all of those solutions, which isn't hard to do. Okay, you can also take a look on the unit circle. Okay, if we go on the unit circle, okay, and we go from 0 to 2 pi, that's one time around. Okay, so if we say, okay, when will the sine of x equal 1/2? And we ask ourselves that. Okay, remember, all of the coordinates on the unit circle have coordinates cosine x, sine of x. Okay, so if we say, okay, let's just solve this on 0 to 2 pi. Okay, my solution's there. Okay, so all I have to do is look at, well, where is my y coordinate 1/2? And notice that happens at pi over 6. Okay, here. Okay, so pi over 6 is one solution. Okay, and then if I just look at the y coordinates, notice it happens again here at 5 pi over 6. Okay, and if I go down here, notice it doesn't happen again. The y-coordinate is not positive 1/2. I get some negative 1/2, but not positive 1/2. Okay, so on 0 to 2 pi, one period of sine, I get two solutions. Okay, the sine of pi over 6 is 1/2, and the sine of 5 pi over 6 is 1/2. And I say, okay, well, what if I want to go on the set of real numbers? Okay, so let's see what would happen. Well, let's see. Let's take these solutions one at a time. Let's see what happens. Okay, so if I'm here, notice at pi over 6, notice I would have to go all the way around 2 pi radians, okay, to get back to there and have another solution. So that would be pi over 6 plus 2 pi. Or I could go 2 times around. I could go pi over 6, 2 pi, 4 pi, okay? Or I could go 3 times around. I could say pi over 6, I could go plus 2 pi, plus 4 pi, okay, plus 6 pi. Okay, so notice that this pi over 6, if I keep adding multiples of 2 pi to it, it'll take me right back to here. Okay, so you represent that by saying pi over 6 plus 2n pi, where n is any natural number. Okay? All right, so if n is any natural number, 1, 2, 3, 4, 5, 6, and so on, then 2n is an even multiple. Okay? And so I get even multiples of pi. So that would be like pi over 6 plus 2 pi, and then plus 4 pi, and then plus 6 pi, and then plus 8 pi, and then plus 10 pi, and so on. So that would represent all of our solutions generated by pi over 6. Okay. Now, let's see. Well, wait a minute. Wouldn't that just take care of a positive rotation? Okay, going counterclockwise. What if I wanted to go clockwise, a negative rotation? Oh, okay. Then n, rather than n being a natural number, n would be an integer. Okay, so that's even better, because now n could be positive or negative, which means that I could rotate in a positive direction counterclockwise or a negative direction clockwise. Okay, all right, so let's see, 5 pi over 6, okay. So if we go to 5 pi over 6, notice again, if I go 2 pi all the way around, it brings me back. So that would be 5 pi over 6 plus 2 pi. If I go 2 times around, that'd be once, twice. So that'd be 5 pi over 6 plus 4 pi. If I go 3 times around, that'd be once, twice, 3 times. That'd be 5 pi over 6 plus 6 pi. So it's the same thing. Okay, I go 5 pi over 6, okay, plus any even multiple of 2 pi, okay, where again we want our n, and notice rather than just going natural numbers, if we go integers, okay, then what happens is it accounts for positive rotations going counterclockwise or negative rotations going clockwise. Okay. All right, so we're going to get into some of these guys today, and I'll keep referring back to this thing. Okay, and you guys already have this in your notes. So let's see what happens. Okay. All right, so this first guy. Well, I've got some similar terms. I've got 3 sine of x and 5 sine of x. Those are similar. And then the -2 and the -1 are similar. So why don't we collect similar terms? And since I want to solve for x, why don't we get the sine of x's together on one side and the constants together on the other side? Okay, so let's see. I'm going to bring this guy over. So I would have 5 sine of x minus 3 sine of x. So that would give me 2 sine of x. Okay, so if I'm collecting the sines on the right-hand sides, I have to collect the constants on the left-hand side. Okay, so I'd get a -2 plus 1, which would give me -1. And then if I divide both sides by 2, notice I'm going to get the sine of x equals -1/2. Okay, so let's see. We can solve that on 0 to 2 pi, okay, or we can solve that on the set of real numbers. Okay, so I'm looking for when is the sine equal to -1/2? Okay, well that's down here, okay? Notice the sine is -1/2 at 7 pi over 6, and the sine is -1/2 at 11 pi over 6, okay? So those two solutions, 7 pi over 6 and 11 pi over 6, are definitely in the interval from 0 to 2 pi, okay? So my two solutions here would be x equals 7 pi over 6 or 11 pi over 6. Okay, but if I solve on the set of real numbers, remember I can just keep rotating around. Okay, so all I have to do is add even multiples of 2 pi. That's it. Okay, so x could be 7 pi over 6 plus 2n pi, or x could be 11 pi over 6 plus 2n pi. Okay, where obviously n is any integer. Okay, that one wasn't too bad. Let's get rid of that guy. Let's bring this guy in here. All right, looks like it's going to be similar to the last one. Okay, so how about I take this 3 sine of x and I move that over and collect it with the 6 sine of x. So if I'm going to move the sine of x's over to the left, I probably want to get the constants over to the right. Okay, so let's see, 6 sine of x minus 3 sine of x is 3 sine of x. And then -5 plus 5 is 0. And then, of course, I divide both sides by 3, so I get sine of x equals 0. Okay, and so we're going to solve that on 0 to 2 pi, just 1 period, and then I will solve that on the set of real numbers. Okay, so we go here, and we say, okay, well, when is the y-coordinate 0? Well, that happens at 0 or 2 pi. Okay, they're the same thing. It happens at 0 and pi, here and here. Okay, so let's see. Here, my solutions would be x equals 0 or 2 pi and pi. Okay, so let's see. Over here, I get x equals 0 plus 2n pi, and x equals pi plus 2n pi, okay, where obviously n is any integer. Okay, and so we take a look there and we say, okay, well, couldn't I just write this as just 2n pi? Because the 0 just goes away. Okay, so I could write that as just 2n pi. Okay, and let's see, how about these guys? Isn't this just all the odd multiples? Because these are even, so if I take any even multiple, 2 pi, 4 pi, 6 pi, 8 pi, and on, and add pi to it, I'm going to get all the odd multiples. Okay, all right, so that's cool. So probably the best way to write these solutions would be like this, okay, where n is an integer. That would probably be the best way, okay? I'm not saying this is wrong up here, okay, but that's probably the best way, okay? All right, so that's pretty cool. I like that. All right. I guess another way to write it, let me see. I'm looking at that and I'm saying, okay, this is all the even multiples of pi. That's all the odd multiples of pi. So couldn't I just get all the multiples of pi and put them together? So couldn't I just say x ends up being n pi, where n is any integer, like that? Okay, there's another way. Okay, so we got two different ways, and I think they're both acceptable to represent your answers. And I think both of these are better than this up here, although technically this is correct. Okay, I like that guy. Let's get that guy out of here. Let's try another one of these. And we got two more to do. Okay, so let's see. Well, doesn't look like there is any similar terms to collect. So why not just get the term with cosine by itself? So I'd take this guy, move it over. Okay, so I get 2 cosine of x equals the positive square root of 3, and then divide both sides by 2. So I get cosine of x equals radical 3 over 2. Okay, so again, now I'm dealing with cosine, and remember, cosine has the same period, goes from 0 to 2 pi, okay? And then obviously I could still keep going and solve it on the set of real numbers. So let's see what happens here. When will the x coordinate be radical 3 over 2? Okay, so we look, well, that happens here at pi over 6. And where else? It happens down here at 11 pi over 6. Okay, so we have some other radical 3 over 2, but notice it's negative here and it's negative here, and we're looking for, when's the x coordinate positive radical 3 over 2. So that would happen at pi over 6 and 11 pi over 6. Okay, so let's see. X equals pi over 6 and 11 pi over 6. Okay, but notice on the set of real numbers, I could just keep adding even multiples, okay, of pi to both of these, and it'll just keep giving me more solutions. So I could say x equals pi over 6 plus 2n pi, or x equals 11 pi over 6 plus 2n pi. Okay, and letting n be an integer, once again, allows me to account for positive rotations going counterclockwise and negative rotations going clockwise. Okay, so far so good. Okay, let's see what happens here. Okay, all right, so let's see. I've got some similar terms, so let's bring this guy over and collect it with the 5 cosine of x. So let's get the constant over on the right-hand side then. Okay, so let's see. 5 cosine of x minus 1 cosine of x will give me 4 cosine of x equals, and when I move that guy to the other side, I get negative 2 radical 2. And then I divide by 4 on both sides. Okay, so that's going to give me cosine of x equals, when I reduce that, I'm going to get the opposite of radical 2 over 2. Okay, so again, let's solve on one period from 0 to 2 pi, and then let's solve on the set of real numbers as well. Okay, so we go back here, and we're looking for when is cosine equal to negative radical 2 over 2. Okay, so when is my x coordinate equal to negative radical 2 over 2? That happens here at 3 pi over 4, and it happens here at 5 pi over 4. We have some other x coordinates that are radical 2 over 2 here and here, but they're positive. We want negative. So that happens at 3 pi over 4, and that happens at 5 pi over 4. Okay, so let's see. My solutions would be at 3 pi over 4 and 5 pi over 4. Okay, so again, on the set of all real numbers, all I have to do is keep adding even multiples of pi there. Okay, so x equals 3 pi over 4 plus 2n pi, or x equals 5 pi over 4 plus 2n pi. Okay, where n is an integer, And again, letting it be an integer rather than a natural number allows us to rotate counterclockwise or clockwise. Okay, so that's a good start to the week. Make sure you keep some version of this handy, because you can see how I keep going back to this. Okay, this guy's really important, whether you're using this guy that I posted today in the notes for the week, or you use the guy that I gave you previously, but you have to have access to a unit circle. All right, guys, that'll wrap it up for today, and I will see you tomorrow. Miss you a whole bunch.